In this lecture, we will look first at electrical systems of a mini hydropower plant, and I am sure that most of the participants have a electrical background, I believe. Therefore, I will not go into very many details because you are already familiar, but I will just run through it because our course should be completed, and so we can't just forget about electrical things. Therefore, but we will make a small change, and first we will look at the electrical systems and generally browse through it, and at the end part of the first lecture that I will introduce to you some that is village hydro systems, where the grid is not available, and then how you can run a plant, or maybe you can design a simple power plant system for a village hydro if there is a request. Right, there is a waterway and they want to generate electricity and use in a village. How we can have a simple system and how to size the component, etc. we will briefly look at. Right. So, in a hydropower plant, in a small hydropower plant, so some of the electrical components we have are obviously the generator, which is connected to the turbine, control equipment, protection equipment, earthing system, transformers, primary distribution system, secondary distribution system as the case may be, and the power limiting devices and metering equipment, etc. Right. And it depends upon whether metering is done. If you are really selling energy, you will need metering equipment of high accuracy, etc., etc. So, some of these things we will briefly look at, but I am sure that you have learned these things in your engineering life, your undergraduate studies somewhere. We will just brush up things in the point of a hydropower engineer. Remember, we are doing this course from the point of a hydropower engineer. So, hydropower engineer is a little bit of electrical, little bit of mechanical, little bit of civil, and a hydrologist also. So, he has to know all the cross section of things that are involved in a hydropower project. So, we will not look it from the point of an expert electrical engineer only. Expert electrical engineer we will use for the final designs and implementation, right. For example, protection systems of the generator, that will be a separate subject which we will not study here, right. When the generator is provided by a supplier, he will provide also the protection equipment, he will not supply only the generator, right. Otherwise, you have to separately coordinate and get the protection systems like say overcurrent, earth fault, and other protection required separately designed and implemented. Usually, we get it from one source, right, we get from one source. So, the most important component, electrical component, is the generator, right. So, nowadays even in small hydros, it is very common to have a synchronous generator, right. But it is much cheaper to have induction motors as generators, what we call asynchronous generators. So, in the smaller power sector like say pico and micro hydro, less than 200 kilowatt like, at the beginning it was very common to have induction generators because they were less costly and also more rugged in construction, and it was easier to source also, right, induction generators. Here is a synchronous generator, right, synchronous generator, and the induction motor as a generator, what we call IMAC, right. So, they have their own advantages and disadvantages, we will see them in a little while, right. So, I think we all have studied, right, synchronous generator. So, in this course we do not want to teach on the operating principles, etc., into details, right. What we know is there is a field winding, rotating field winding, which is usually nowadays supplied by a generated electricity from a 3-phase winding mounted on the shaft, and then rectify it using rectifiers, rotating rectifiers, and then field is created which is rotating. So, usually brushless, right, brushless type. So, that we generate DC for the poles to be magnetized. It may be 2-pole machine, maybe 4-pole machine, maybe 8-pole machine or whatever, and then all will be magnetized using this DC created by rectifiers, which are also rotating and mounted at the end of the shaft, generator shaft, right. So I think all these things are normally quite familiar. We have an automatic voltage regulator, right, and then where the set point is adjusted, right, and then we can generate whatever the voltage that we want to generate. Usually in hydropower schemes, say less than 1 megawatt, right, less than 1 megawatt approximately, you can even generate voltages at 400 volts or 415 volts 3 phase, right. But you can see when it is 1 megawatt at 415 volts, currents may be rated currents may run to 1400 amperes, right, pretty big currents to be handled, conductors to be sizable. Therefore, when the power capacity increases, right, generally the generating voltage will increase to about say sometimes 3.3 kV or 6 kV, etc., because otherwise the conductors will be too large to handle the current, right. Therefore, we have a new situation, because your generation voltage is now 3 kV or 6 kV, right, and then if you want to have a station supply which has to be 415 volt for your own utilization, you will have to have a separate transformer, because you are generating at say 6 kV. So, you will have to have a 6 kV to 415 volts step down transformer for station use, auxiliary transformer, right. So, in power plants we have this situation, because it is only in small power plants less than 1 megawatt we can generate at 415 volts, right. Otherwise, it is not very practical because of the heavy currents, right, because of the heavy current. Otherwise, the generator becomes too expensive. You need to have thick conductors for the windings, stator windings, to generate and run currents in the order of 1400 amperes, right. Therefore, in power plants you will see power generation is not at 415, but at a higher voltages like 3.6 or 6 or something close to that, right. Different manufacturers have different suggestions for the voltages. Of course, you can request I want this generation voltage, but in that case what happens is these generators are, remember, specially manufactured for the plant, right. You can't use an existing generator anywhere, right. You will have to have a special generator manufactured for this particular plant, because speed will be different and the capacity will be different and the voltage you require will be different, right. Here I have put a exploded view of a 4-pole machine, right, 4-pole machine. I think you are all familiar with this. Rectifiers will be mounted at the end of a chamber here, rotating rectifiers, right, which will be here is the exciter winding, right, AC, and it is rectified by the rotating rectifiers, right, rotating rectifiers, and then fed to the field, right, fed to the field, and the stator is here, right. But as the number of poles increases, that is the issue, because the turbines normally run at 750 and so on RPM, right. Then you need large number of poles, then the generator becomes more and more expensive. If you look at large power plants like 100 megawatt, 150 megawatt, their speed may be 400 RPM, right. Therefore, the number of poles will be quite large, because to bring down the speed, right, quite large. So, the gas turbines etc., by the technology they are high speed machines, Therefore, they can run with maybe 2 pole, 4 pole machines. So, they are cheaper, size is smaller. So, this induction generator, I think the principle of operation we all know, rotating magnetic fields and creation of the 3 phase and so on. But the only issue is when it is run as a generator, you need a reactive power supply, right. You need to have a separate reactive power supply, right, and which is usually by a capacitor bank, 3 phase capacitor bank. So, you have an additional cost and also maintenance cost, right, maintenance cost of the capacitor banks, right. And so, other than that, induction generators are also can be used for small scale projects, small scale projects. But when you have to that generate electricity and sell to the grid, etc., grid will, we are going to see the grid codes in the in one of our discussions, where the requirements of the utility have to be considered. Utilities do not want usually large induction generators to be connected to their system, because of their system quality issues, right, quality issues like various problems that might be created by the large induction generators. Therefore, they always prefer synchronous machine. So, grid code will say if the machine is larger than certain capacity, you must have synchronous machines. We will look at a typical grid code used in Sri Lanka, but it may be different from utility to utility. So, if you are working with any utility in India, you will have to look at the grid codes published by them before connecting any embedded generator to the system, right, embedded generator to the system. And another limitation is, that I am sure that you are familiar with the distribution, the distributed concept of distributed generators, right, concept of distributed generators. Another issue that might arise when you are sizing your plant is grid connectability, right, grid connectability, right. That is, now you can propose at such and such a place I have a waterway, and I think we looked at this contour maps and say we can identify projects. So, we identify a project at a remote location. Now, we want to put up a power plant and sell electricity to the grid, right. Now, the grid operator will have numerous problems. One issue is whether at all he has a transmission line close by or grid substation close by, and also if the grid substation has additional capacity, already there may be several power plants connected to it, right. Already there may be several, maybe wind, maybe solar, maybe hydropower connected already to that, because these power plants are connected on the load side, distribution side, right. They are coexisting with the loads and consumers. So, I will show you a typical arrangement here, right. So, if you take a typical grid substation, maybe even India. So, I will take a typical grid substation. Say if the incoming voltage is say 132 kV, usually it is stepped down, for example, into 33 kV as the primary distribution, right. There may be 2 transformers. And then in the substation we have the bus bar system. Breakers, by crosses I am indicating the breakers, right. And then you have the outgoing feeders. This is not an exact diagram, I am just drawing approximately. It may be different from different substation to different substation, right. So, this is the 33 kV distribution system, right. So, loads are connected to this, right, loads and distribution transformers are connected to this with various feeders. So, maybe for each village a line is going, and then a step down transformer will be there to get 400 volts, right, for village 1, for village 2 and so on, every feeder will give supplies to that. So, now we are proposing to connect small hydropower plants and also solar plants and wind plants, right, to this distribution line. So, we want to put up a generator here. One megawatt power plant, right. Somebody else wants another one, another 2 megawatt one, right. Someone else wants another 5 megawatt, right, and these transformers are usually 31.5 MVA. Let us assume there are 2 transformers, right, 2 transformers are there. Normally, transformer distribution substations are designed with N-1 criteria. N-1 criteria means one fails, still system can be managed. So, if one transformer is under maintenance or repair, still you can fully supply the system, right. So, usually 31.5 MVA transformer can supply about 25 megawatts with a suitable plant. If you take a 0.8 like power factor, so you can give about 25 megawatt loads altogether. So, you will make sure that your total loads here with a suitable diversity is not exceeding 25 megawatts, right, otherwise you can't supply, right. And now, they see the situation, now you are adding up various generators here, right. Now, suppose there is a day which is due to whatever reasons people are not utilized, maybe a daytime in a weekday, all the people are at work, right, their consumption is now minimum, because during a working day, right, almost all the people are going to work, home loads are very minimum. Therefore, in this system consumption is minimum now, right, consumption is minimum. Then what happens? Now, suppose that is a very rainy day or whatever, right, generation is maximum. These generators generate maximum capacity, right. Now, if you have many such machines, what happens? Now, consumption is very small here. Therefore, now the power flow goes back to the transmission system, reverse power flow happens, because the generation in this side is much more than the consumption, right. Therefore, power begins to flow upward, reverse power, right. But suppose if we have too many generators connected here, then you might exceed 25 megawatt, right. Now, the transformer does not have enough capacity to allow all the generation to go up, right. Therefore, utilities will have a limit when you have 2 transformer system, each having 25 megawatt 2 transformers. All the addition of all the generators, right, has to be less than 25 megawatt, right, has to be less than 25 megawatt, right. That is together mini hydro, solar, rooftops, all together they will not allow it to exceed 25 megawatts. Now, you go with a proposal, I have such and such a place, mini hydro opportunity of 5 megawatt, I am interested in developing. So, you have to first make an application to the utility to check whether your nearest grid substation has extra capacity, right, to see whether your nearest grid substation has extra capacity available. They will check whether already transformers are already the system is full of mini hydropower plants, then they will say sorry, we can't, this we cannot grid connect, right, this we cannot grid connect, because of the substation capacity is not enough. This has happened particularly in areas, in hilly areas there are many hydro opportunities, no, and therefore, they have been developed, but the grid substations are limited, right. So, if the government or the utility want to accommodate more mini hydros, they will have to augment this grid substation with another transformer, another 31.5 MVA transformer, right, which can take another 25 megawatt. So, when you have 25 into 3 with n minus criteria, when you remove one, other two can operate, then you can accommodate up to 50 megawatt. Then you can accommodate mini hydros and other power plants up to 50 megawatts, right. Then grid connectivity again comes up possible. So, for that you have an expenditure, augmentation expenditure of the new addition of new transformer, right. But keeping the n minus 1 criteria, you will have to check whether the plant is grid connectable, right, before doing other investments, etc., right. So, otherwise you will have to reduce your size probably. You proposed a 5 megawatt one, they will say we can allow only 2.5 megawatt, only capacity, extra capacity available is 2.5 megawatt. So, reduce your size, right, reduce your size. Remember this part therefore, right, you have to check the grid connectivity of the power plant, right. So, this shows the principle of an asynchronous generator, that is the induction generator, right. Again I will not go into details, I think you have already studied it, right, and various control strategies are there, and about this reactive power supply and the cheaper ways of doing it, etc., etc. But I think you can separately study if you want, but induction generators we rarely use in larger small hydros, right. So, it is just for the information I have put, because there may be non-electrical engineers in the course. So, in that case for their benefit I have put the components of a induction machine for their information. They can of course read something and study more. So, these are called squirrel cage type, right. Squirrel cage is this one, where the ends of the conduction bars are short circuited. So, here is a comparison between this induction generators and synchronous generators, right. So, synchronous generators generally competitive in high power range over 100 kVA, right. Not readily available, synchronous generators are not readily available, you have to order and buy, right. Complicated and liable to break down, right, and high maintenance cost therefore. Needs to be ordered, as I said earlier, they are not readily available, you have to order it, right. Self exciting, that is an advantage, can supply reactive power, right. Usually mini hydros are not expected to contractually not expected to provide reactive power to the utility. For large private power plants, yes, for large private power plants there is a contractual obligation in the power purchase agreement, when requested by the utility the owner should provide reactive power, right, the owner should provide reactive power. But for small hydropower plants and small other solar and so on, there is no mandatory requirement to provide reactive power, although the synchronous generators can provide the reactive power. Therefore, small hydropowers power plant owners usually try to operate the power plant at unity power factor. Why is that? Why? What is the advantage of operating the small hydropower plant, right, at unity power factor, right? That is because then you will reduce your own losses, because you will generate, your small hydropower plant will generate, and then you will have to step it up to the 33 kV or whatever distribution voltage, right. Now, if you are operating at a different power factor, your losses in the transformer will be high, right, your losses in the transformer will be high. Therefore, you are wasting your energy which you can otherwise sell. Therefore, it is always advantageous to run the machines at unity power factor, right. So, they purposely therefore try to run close to unity power factor, because there is no mandatory requirement for providing reactive power, although the machine can provide. Higher full load efficiency, good part load efficiency, right. So, as we discussed earlier, typically they run into about 96%. Higher rotor inertia, that is also good, because the higher the inertia, the better for the frequency stability, right, better for the frequency stability. Good voltage regulation, good overload and motor start capacity, can be made to sustain short circuit and clear fault, fairly simple selection and the calculations. And some properties of induction machines, induction generators, generally competitive in small power range, maybe less than 30 kVA, readily available in small range. You can go and buy from the market an induction generator or induction motor. Induction motor you can use as a generator, right. So, they are readily available for many applications, they are made, and therefore, they are readily available. Rugged and simple, reliable and low maintenance cost. External source needed to supply reactive power. Capacitor banks are required usually. Lower full load efficiency, poor part load efficiency. Low rotor inertia, poor voltage regulation, de-excites under short circuit and might need remagnetizing. I think you remember that the voltage build up in an induction machine happens because of the magnetism, right, in the core, right. There should be a magnetic properties in the material, so that initial voltage build up can happen, right. Sometimes de-excites, therefore, it will not build up voltage. Therefore, using a DC source, we will have to remagnetize sometimes these induction generators, if it de-excites and voltage does not build up. And that depending upon the way the field winding is provided with electricity, they are brush type and brushless. Brushless is the most common now, right. Rotating armature type, brush type generally not preferred in mini hydropower due to high maintenance cost. So, this is normally not, although they are technically possible, they are not used. Rotating field type, brushless type is the one that we are now using. Exciter armature is mounted in the same shaft as that of the main generator, and AC voltage generated in the rotating exciter armature is converted to DC voltage through the use of 6 rotating diodes to feed to the main generator's rotating field winding. This is a typical arrangement. I think in the photo figure also we already looked at that, right. So, cylindrical rotor type and salient pole type synchronous generators can be used, but in small hydros, because of the low speed, we might have to go for salient pole type, right. Cylindrical rotor type 4 or 2 pole machines are high RPM, 1500 3000 RPM for 50 hertz, and invariably used with steam turbine, gas turbines, because in steam turbines and gas turbines you get the necessary high speeds. Salient pole machines are generally low RPM type and generally manufactured in RPM range starting from 148.8 RPM and up to 1000 RPM for a 50 hertz system. So, in the projects we did, I think our rated speed was something like 750 RPM. So, we used, I think as I remember, salient pole machines for those. We did not use a gearbox. One option is to have a gearbox and to increase the speed to higher levels, so that you can go for even cylindrical rotor machines, right. But then you have the question of buying the bearing the additional cost of the gearbox as well as maintaining it. Gearboxes have a lifetime of about say 10 to 12 years. So, after 10 to 12 years you will have to replace them. So, there is an additional initial cost as well as an operating cost and the maintenance cost, and then the replacement cost every 10 to 12 years. And now, for a given site, now your site you have decided where it is, at what altitude your powerhouse is, and what temperatures are existing there, and all these things are now you know from your site, right. And also whether you are going to have a village hydro or a kind of a small one, and non-grid connected plant or grid connected one, still you know, right. So, then we have to consider 4 factors, right. temperature factor, altitude factor, electronic load control factor, that will come only if it is a village hydro kind of a non-grid connected one. So, this is for non-grid connected. I will explain a little bit of that later, and then the power factor. So, the generator KVA will be installed capacity in kilowatt, that is the turbine capacity, right, divided by A, B, C, D. I think as electrical engineers we know that, but the temperature factor and the altitude factor you may not be that familiar with. Let us look at some typical values. Here are some typical values. These are not hard and fast rules, right, but you can get from handbooks, right. So, you can see the temperature factor, right, temperature factor. So, so this is designed for 40 degrees Celsius temperature, then your temperature factor is 1, right, 1. But if it is higher, then you have to derate your machine. If they are going to operate at a temperature of 45 degrees, right, 45 degrees, then you have to sacrifice about 4% of the capacity. So, you will have to have extra 4% capacity. So, you have to divide the kilowatt turbine capacity divided by 0.96 to get the KVA, capacity rating of the generator, right. If it is lower, of course, you have the advantage, right, you have the advantage, you will have a smaller size. Then you can see the altitude factor, right, altitude factor, right. If you are your plant is at say 1000 meters, normally they are designed for 1000 meters, at 1000 meters altitude factor is 1, no change, right. But if it is 2000, 0.93, you have divided by 0.93, right. Why the altitude factor is mattering in the generator selection, generator capacity? Because as you go high in altitude, air density decreases, right, air density decreases, and therefore, your cooling, generator cooling effectiveness goes down, right, generator cooling effectiveness goes down as the air density goes down. So, higher you go, lower will be the density, and therefore, lower will be the effectiveness of the cooling system of the generator. So, you have to have an additional capacity for that, right. You can see if it is say 4500 meters altitude, then you will have a substantial increase in the required capacity. Your altitude factor is 0.77, right, 0.77. So, these are typical values I have put. Maybe you can look for a even big higher altitudes from a suitable handbook, right. And electronic load control factor comes in only for the non-grid connected power plants, which are usually village hydro kind of things, right. So, we normally have about 0.83 additional, right, capacity. So, if it is a village hydro, you have to put a 0.83 inside in the generator. So, this will be generator capacity finally, right. So, if it is a turbine capacity is 1000 kilowatt, so it will be 0.96 into 0.93 into 0.83, right. And if your power factor you want to operate down to 0.8 up to 0.8, right. So, this will be the KVA rating of the required generator, right, required generator. So, it depends upon the altitude, operating temperature, whether it is a grid connected or non-grid connected, where you have a electronic load controller, and the required power factor. Because even though we try to operate at unity power factor, due to some reason we might have to run on 0.8, right, due to some local load requirement or whatever. So, you should be able to. So, then you can see your generator capacity is substantially larger than the turbine's kilowatt output. Turbine always give out kilowatts, right, kilowatts, and then generator has to be resized to kVA because of the reactive power involvement, magnetization involvement. So, the generator size as calculated above is multiplied by about 30% allow for the following conditions. So, normally once we calculate, we keep it practically about 25-30% extra capacity for these reasons. The output of the turbine could be higher than expected due to better design. Sometimes although the turbine manufacturer says I will give a 1 megawatt machine, he will generally design it for 1.1, 1.2 to be on the safe side for him. So, if you have extra capacity, you should be able to utilize that, right, you should be able to utilize that. So, better to have a little bit bigger generator, and if the large motors are supplied by the generator should be able to handle the starting currents of especially the induction motors. The generator is always generating rated power when using an electronic load controller. We will see how it operates when you have electronic load controller. In the next slide also we will discuss. So, the induction generators, squirrel cage induction motors run as induction generator, right. Induction motors when rotated above its rated synchronous speed, I think these things are known to you as electrical engineers, by some prime mover, hydraulic turbine in case of mini hydropower, and fed required excitation through capacitors or through import of reactive power from grid, generate electrical power. Slip in such case is negative. Very rugged construction due to general ruggedness of squirrel cage rotor. Practically, though induction generator is cheaper in range up to 30 kVA in size, synchronous generator is preferred over induction generators in size about 10 kilowatt due to practical considerations. Induction generators, however, use almost invariably in Pico or Pelton electric generators set up to 5 kilowatt. Very small cases, to keep the cost down, we go for induction generators, but our topic here is small hydropower which are running say about 200-300 kilowatt definitely. Therefore, we will not consider induction generators as candidate for such power plants, right. So, as control equipment, we have the voltage control equipment, right, compound in transformers for voltage regulation in the range of plus or minus 5% for generators up to 125 kVA. Otherwise, nowadays we use automatic voltage regulators, and the frequency control equipment, electronic load controllers up to installed capacity up to 1000 kilowatt. Otherwise, hydromechanical, electronic, digital governors for installed capacities above 100 kilowatt. These electronic load controllers are used for non-grid connected plants, right. So, this idea is this: now in non-grid connected plants, your loads do not match with the generation, right, because it is usually a village hydro and village loads are connected. So, you are always generating, there is a generating mismatch, right, generating mismatch. So, when you have extra of obviously, when your loads are more than the generators, you have to drop loads, you have to cut off loads, that is the only way, right, you have to disconnect loads. But when your generation is more than the loads, in village hydros and very small schemes, what we do is we connect some loads, artificial loads to discharge the energy, usually immersion heaters, right, usually immersion heaters. So, there are immersion heaters immersed in water, usually with the same flowing water, and if the frequency tries to go up or if the speed of the machine tries to goes up, we will send the speed, right, and then switch on or switch off immersion heaters, right, until the frequency or the speed becomes stable, right, so that you maintain the frequency or the speed of the machine, right. So, an equipment which allows constant power generation, no flow control, and maintains constant system frequency by dumping additional generated power to electric immersion heaters used as ballast. Electronic load controllers are considered to be cheaper alternatives of costly flow control governors in case of mini hydropower or micro hydropower. Since electronic load controllers use thyristors as switching devices, many harmonics are generated requiring derating of generator. That is why we had to divide it by 0.83 because of the harmonic generation. But these are applicable only for pico hydro or micro hydro kind of a small application which are non grid connected and which can be simple, construction can be very simple and costs are reduced, right, costs are reduced. So, here is a off grid system, typical system, right. So, we have the this is only one possible configuration, there can be many other configurations. You can see the diversion loads, these are the immersion heaters, right. So, we get the output and then the DC output is inverted again, right, to stable frequency and voltage and supplied to the grid, right. I am sure as electrical engineers you are more familiar with these things, right. So, we will not go into the deep analysis of these things, right. Now, I come to a slide 2 to describe the controlling of this the power generation in a run of river scheme. In a run of river scheme, we have the flow rate varying, right, from day 1 to 365 days flow is like this. So, this will be the flow coming into the, this is the forebay tank, what is coming into here Q, right. This is the one they are generating, turbine is generating which is connected to a generator, electrical generator, right. So, now what happens is this when the flow goes up and down, right, unless you increase and decrease your water usage, this water level at the forebay tank try to go up and down depending upon the flow rate. When the flow rate goes down, it tries to go down. When the flow rate is increasing, it tries to go up and even can overflow, right. And depending upon this variation, therefore, you need to open and close your needle valves or wicket gates. Needle valve in case of impulse generators, wicket gates in case of Francis and Kaplan machines, right. So, therefore, we have a water level sensor here, right, a water level sensor here at the forebay tank, right, a water level sensor. So, water level sensor will sense voltage, sense the level and send it to a water level controller here, water level controller. So, water level, it may be a 4 to 20 milliampere signal or converted to voltage, a voltage signal, right. Sometimes it is a wired connection along the penstock pipe, maybe it can be done with the radio connection also. Anyway, the signal is coming here. So, if the water level controller says water level sensor says the level is going up because of the increase in the incoming water, then he will open the needle valve. Controller will send signals to the needle valve open, right, open, and if it is going down, it will say to the controller, right, close, right. So, I will read this. A water level controller in a mini hydro power plant regulates the water level in the forebay or afterbay to ensure stable operation. The control system uses the water level as an input variable and act on the opening of the wicket gates or nozzles of the turbine. Here is an schematic view, right. You can see the water level sensor in the forebay tank, right. It is a wired or radio link comes to a water level controller, right, and water level controller will give signals to the hydraulic control system of the nozzle, because nozzles have to be forcefully handled, that you need force, therefore, you need to have a hydraulic system to handle it. So, this hydraulic control system will get the pulses from water level controller and which will open and close the needle valve and the wicket gates, right, and the wicket gates. So, this part is in the powerhouse, this is far away, this may be 1 kilometer distance. Usually there is a wired connection, right, wired connection. I will not go into further details of it. These are electronic units, water level control. Sometimes they come as water level control alone, sometimes it is coming with other functions like say various other protection functions of the power plant. They can be integrated into one unit, right, integrated into one unit like say over frequency, under frequency relays, all can be combined to one electronic unit. So, that the cost of the power plant can be reduced, and nowadays there are such integrated devices. It provides the water level controlling function and additional functions also. So, you do not have to invest in separate components for each function, right. So, there can be multifunction meters or controllers which can be used for many functions, among which the water level controlling is one, right. We have discussed lot of things, but we must see practically how these things. Ideally we should visit during such a short course, we should organize a field visit to a small hydropower plant, then it could have been more meaningful. So, this is this photo was taken when we first visited the site. So, I told you we do all the things using contour map. So, we did all this initial work from home, from office, and we were convinced that there is a project. We made even an application for the site allocation. Then we went on in a early morning through the jungle. You can see all jungle. So, you have to go through elephant tracks and other things using animal tracks, following carefully, right. So, we came to this is the possible location for our diversion weir, right. We came to it going through all these jungle areas, right. This is one of my civil engineers. Same location from downside, right. So, those days there were no digital cameras. This is in early 2000, no digital camera. So, we use the analog this that what is real type cameras, and we print them and then we stick them together to make the entire cross section. You can see several photos have been stitched together to get our required views, right. You can see we are stitching together photos to get the real picture of the location, right. So, these photos are random. So, this is the canal under construction, you can see not finished yet. We are you can see this section is still under construction. Here reinforcement you can see, here you can see. Sometimes we put this stiffness, but when you have long sections, some stiffness to make sure that the walls will not be collapsing, so that this regularly we put stiffness on the canal. Sometimes we cover, you can see the stiffness, you can see all along. This is under construction. Some visitors coming. This is a overflow provision, right, overflow provision. Where water can overflow and then go out here, right. Here you can see our diversion weir was under construction. This is long along there, but still this part has not been closed. So, it is under rainy day, you can see the flooding water, that is ferocious water flows. So, you have to work under very careful conditions when you are working on mini hydros. In the sites you have to be very careful, right. These conditions are not easy. Same place, the more water. So, we build the weir on this rock, pin to the rock, right, pin to the rock. Here you can see. So, this is the start of the canal, right. The canal will begin here, right, canal will begin here. This should be connected to the canal. so that the water can flow into the canal. Sometimes we box it, we call them boxing it, completely cover it, because this soil is liable to be to fall into the canal. Then your desilting arrangement is going to be difficult. A lot of silt and soil comes in, right. Therefore, we want to avoid that. We will completely cover it, those sections, right. Sometimes we have to go on supports, canal has to go on supports when you are crossing, especially streams, right. You will have to have some supports and run it on supports. Here this entire section you can see running on supports. Here a desilting basin, I think I showed this photo earlier also, not with this view, right. You can see the desilting basin is being constructed. You widen the canal to reduce the speed and thereby drop in the particles here. So, this is the water fall that we trapped, but we did not use this part. We did not use this part because there is a observation gallery somewhere here, where people come and see the waterfall, right. Therefore, in the environmental study we were granted to use water from down somewhere here, where people cannot see. So, the visible part we allowed. So, these are the environmental compromises we have to make, right. You can't use because people are coming here, all the tourists, everybody comes to see this. So, if we just constructed the diversion via here and closed down the waterfall, that is a real big issue. So, we started somewhere here, this part we left. Otherwise, it could have been a 10 megawatt project. So, we had to limit it to 4 megawatts because of the other environmental requirements. There was a, remember these things also, there was a planned water project upstream, right. It was not implemented, but when we applied for the permission from the water board, they said we have a water scheme to be done in 10 years time and we want so many million liters a day. Therefore, we kept provision for that also, because our power plant is going to be 30-40 years lifetime. So, if we unnecessarily make a large power plant, after 10 years you do not have water, enough water. That is why we constructed a 4 megawatt plant rather than going for a larger plant. We kept for the allowed for the environmental reasons, the visible part of the fall was allowed to be to continue, and also allowed for the water board requirement, annual water requirement for the future. Now, the water project is done. Now, the water project is done for a nearby town, they tap water from the river, but we are not affected because we kept provision for all those things. So, lot of rock blasting etcetera, because you have to take the canal on the same level, right. So, you have to remove all the barriers, rocks and everything, and come level it to your requirement. So, these are the supports being constructed for the penstock supports, right, penstock supports. Here you can see all are penstock support. Now, on that the penstock erection will be done. So, waterfall you can see from far away. Here you can see this is a shot taken from far away place, right, but you can, this part was untouched, right, this part was untouched. This part was untouched, right. There was a water board pipeline, right, that was a smaller one, but now they have put a bigger one. This is where we constructed the measuring weir, right. See, they are pinning it to the rock. The difficult terrain, this area. Here you can see the observation gallery. See, this is where the tourists come and see the waterfall, right, and observation gallery. This is one Norwegian, he is no more. I learned lot of things from him, right, because he was a director of our company, but a civil engineer and a very thorough knowledge on mini hydropower development. So, I went to Norway and learned lot of things from their power plants and from their design teams. It is very hot for him in Sri Lanka. You encounter these kind of things, wasps, right, dangerous. So, you have to when you are doing hydropower etc., in jungle areas, you have to be very mindful. This is the measuring weir we looked at earlier also. We had lot of opposition from villagers at the beginning for doing a power plant here, right. So, there were a lot of political interventions, right, and so we had to take them to the site, politicians and the village leaders. You can see in my young days, you can see me here, and take them and show them what we are doing and how they will be affected etc., right. So, this is such a visit. So, doing mini hydros not easy, because lot of involvement is there, lot of lands are involved, lot of people are affected, right, not like doing a small solar power plant. This man said, I will never allow this plant to be done, right to my face, right. But finally, they all agreed, we got them there and got them convinced that we are not harming their area. See the amount of work that we have to do, various construction work, excavations, lot of civil work. Penstock under construction, you can see the stretch, the penstock is going up to here, right. This is a penstock path, right, penstock path. It is a 550 meter penstock, right. So, we can design them office, all are easy, but with the real construction is not that easy, right, not easy. You can see here these rollers are placed, these are rollers to slide the pipe without damaging them, right, without damaging them, and some are hung up, you can see, so that they can be lifted down without damaging the pipe surface. And so, this is, you can see all the pipes are being aligned. Now, this is after welding, right, this section has been completed, you can see they have even put this anti-corrosive or other paint scheme on the welded areas. So, you can see the supports are here regularly. Here I think I showed you earlier how you keep it on supports, right, either a steel piece, smooth steel piece with grease, or otherwise a nitrile kind of a rubber, strong rubber piece, to avoid, because in the expansion it will move up and down and thereby the paint will get damaged. You can see this from the top, this is the powerhouse here and the penstock is still being done. Here is a expansion joint, right. I told you expansion joint which are normally kept at the upper end of just below a anchor, just below an anchor, right here. So, they are tightened, so that there are two rubber flanges here, so that they will be fixed and no water leaks can happen. So, inside the pipe is having a gap, right, inside the pipe is having a gap, right, in order to allow for expansion. Here is the bifurcation, single pipe comes and divide into two. So, this is the bifurcation we got specially fabricated, right, and it has many webs because it has lot of forces. So, the forces should be distributed to the anchor. There will be a big anchor coming here to pin down all the forces down to the earth. So, this is where it enters the powerhouse. Here is an anchor. Whenever there is a slight angle in the pipe, you must have an anchor, it is necessary. It can be a vertical one or it can be a horizontal angle. Here is a welding being done, right. It should be a X-ray quality weld. So, welders, we have to get them qualified, tested and qualified for X-ray level grade testing. Normally dockyards and there are testing agencies who can test them. They will ask them to do samples and then see whether there are inside air pockets and other deficiencies, defects, right. If they cannot do a continuous thorough welding, they are not qualified as X-ray quality welders. And even after doing this, we will keep not maybe on every joint, maybe on a select 10%, 15% joints, welds, we will keep an X-ray source inside and take X-rays and see whether the joint is okay, because it is critical, because they are subject to heavy pressures, right, can be damaged. Here the inside of a anchor, I discussed earlier. Here you can see the bifurcation where the water is divided into two pipes, one from one pipe. They are lining, and this is where the pipe enters the power plant. So, this is the main inlet valve which comes from the manufacturer of the turbines. He will provide all these things, and now the pipe has to be connected to this main inlet valve. Therefore, you have to get an extra flange from the manufacturer of the this main inlet valve and get it and weld it to the pipe end, because it should exactly match with the main inlet valve's flange, otherwise you can't connect, right. So, therefore, you get an extra flange from them and hand it over to the contractor who is doing the penstock, and then coordinate so that they can do it together, so that they will match, otherwise you can't connect it, right. They should match exactly. So, this will be this part has to be smoothly connected here with a good bend. Here is another bend. You can see the foundation of the anchor is done already, and some reinforcement also you can see. Now, on top of this they will complete the anchor. Now, you can see fully finished, fully painted, right, fully finished and fully painted, otherwise corrosion will develop inside, even inside the concrete, right, because there may be defects in the concrete, and therefore, maybe water and other things, moisture can accumulate and finally damage the pipe, right. Therefore, you must thoroughly finish it with the approved paint scheme and then do the anchor on it. Here they have done the smooth connection, you can see at the powerhouse entry. They have welded pieces together, pipe pieces together to make it a smooth finish, and then you can see they will finish connect the flange here. And there at the powerhouse entry there is a big bend, you can see. Therefore, this section will be complete here another anchor. You need to concrete this entire pack, right. From this point onward, all these areas have to be So, that will be integral part of the powerhouse, anchor will be integral part of the powerhouse. They are welding, you can see how a bend is welded. They first tag it, the pieces together. These pieces we got from the pipe manufacturer himself. We gave the specification of pipe pieces to cut into certain angles, right, as required. So, we got many of them, so that we can make the bends, right, we can make the bends. So, he is an X-ray quality welder, right, and both of them. So, they from this side and maybe they go inside and inside also they weld. Now, they are doing the bifurcation welding, you can see bifurcation, 2 pipes have been joined to the bifurcation piece. Here once it is finished, but the anchors are to come yet. We kept a opening here. This part can be removed by removing the bolts. That is, someday if we want to inspect this section of the pipe, there is no access. Whether the corrosion is too much after 10-15 years, if you want to access it, you can't come from the top, neither you can come from the bottom, right. So, at the middle point we kept a piece here which can be removed by removing the bolts, right, and therefore, you can have an access and inspect the penstock if required. Sometimes we put these clips to hold it down, right, in case any problem occurs. So, this place has to have a big anchor, but you can't do it, lot of landslides happen. This entire, because of the rains, these sections they collapsed here. So, we have to remove all these things again to do the anchor here. You can see it was a difficult area. Here now it is done, anchor is done once, same place. I can see upper anchor also here, anchor, and then you can see the expansion joint here. Here they are fixing an expansion joint, you can see it. So, these 2 flanges will come here and there will be the rubber packing here, So, there will go and then the bolts will be connected and tightened, right, tightened. Here this is the path for the cable coming from the water level sensor to the water level controller in the powerhouse. We have a power line also to take power to the forebay tank. So, the forebay tank people can have some electricity, right, otherwise they will be in dark during night time. So, we have power lines as well as this signal cable which is taking the water level sensor signal to the powerhouse water level controller. Here now they have finished the anchor on the bifurcation, right, on the bifurcation, and the 2 pipes are painted and completed. Here on the upper terrain also now it is completed. Here you can see the expansion joints here and here. Here the transportation, you can see I told you it is sometimes economical to have several diameters and transport them inserted within that. So, that your transport costs, both shipping cost as well as land transport cost will go down. Otherwise, if you can put only 3 pieces otherwise, right. So, you have to go here, they have 3 pieces inside. So, you can see otherwise you have to go for 2 extra trips, right, 2 extra trips and 2 extra container loads, right, because if you do not do this. So, you have to economize, right. This is the powerhouse construction site. You can see some foundations for the columns. Here you can see the columns have come up and then we have a horizontal beams here, right. That is for the crane beams to be kept. You need a crane for the powerhouse to lift the generators and then to connect them, align them. So, they are this I will see some other photos also. Crane beams will come on this level. We want powerhouse to be having a heavy weight, right, because you know that when the pressure from the penstock water comes onto the powerhouse, it should not slip. So, it should be well pinned to the ground, because you can see the penstock surface will have such a big pressure and push the powerhouse down. So, it should be very well connected to the ground or to the rocks, right. So, we have the concrete mass will make sure it is heavy and connected to the ground. Here is the tail race, right. So, this is the powerhouse flow level. So, and the water will, there are two turbines here. So, the water will fall and then go out in this way, this side back to the river, right. We kept it completely underground. So, finally, all this place was covered and it was not visible. So, it can go underground to the river back. This shape was my choice. I decided to have this shape identity for our power plant, all the power plants. Here they are taking the crane beams. On these beams the crane will move, right. So, they have to be kept on the horizontal beams, concrete beams. Here you can see these are the crane, this is the crane beam, the pieces put together and connected here. The crane beam will be, cross beam will be like this, they will run on these steel beams, right. So, this is how you connect the powerhouse and the other things to the rocks, right. So, you put all these things and then the grouted, put in the hole and grout poured. Therefore, it is a solid connection, and then on top of this we will concrete. Now, they are installing the turbines and the generators, right. He is my mechanical engineer, he is my electrical engineer. White helmet is as usual, I think you are also following engineers, others are the supporting staff. Now, here you can see this casing. Here it is open, right. So, this entire part has to be concrete. You can see some reinforcement also coming from the floor, right. So, once everything is placed, this section will be completely concreted. So, that the turbine and the casing will be completely fully connected to the powerhouse building floor, right. So, you can see later on how it is connected, see, and this is where the penstock will be connected, and this is the water entry path, right, water entry path to the turbine. So, the turbine housing is this. Here they are connecting it. Here you can see this part is complete to be concreted later on, once all the adjustments are done. So, this part will be fully concreted, so that the turbine housing and the fully structure will be fully connected to the powerhouse floor. Here you can see now the generators have been kept and connected to the shafts are connected, right. There are yellow one are the turbines, red one are the generators. There are two units 1.25 megawatt each. These are the turbo turbines, right, turbo turbines. These are the hydraulic units to control the needle valve movement, etc., right. So, they get the signals from the water level control and the control system, right. So, they will put the necessary pressures required, hydraulic pressures required for the needle valves to move in this case. Otherwise, in Francis machine it will be wicket gauge to move. Here you can have a better look at the turbo turbine being constructed. This is the outdoor switch yard where we want to step up to 33 kV, right. We here in this plant one machine is 1.25 megawatt, we decided to generate at low voltage 415 volts. So, it is a 415 volt to 33 kV step up, and that is where we sell electricity. Here the tail race is being further constructed. This is the switch yard, right, switching equipment, lightning arresters and the main breakers etc. installed. Here the one set is almost finished, right, almost finished powerhouse area. And here you can see a device here, right. This is a weight, right, lifted up and kept there, because you can see now say the power plant is in operation, right, power plant is in operation. Now, power plant is in operation, right. Now, while the power plant, now water comes, say rated power water comes in the here water rated power flow was 1.6 cubic meters per second. So, each machine took 8.8 cubic meters per second, right. And now, suppose is in smooth operation. Now, the utility circuit breaker trips due to a network malfunction, right. Something has happened on the network side and your breaker trips. Now, look here, now water brings energy, you can't stop water instantaneously, right. Water brings energy and now impart to the turbine, and generator cannot take out the energy because the breaker is open. Now, there is a big mismatch. Only choice is rotating parts to overspeed and take the kinetic energy to increase, and that will destroy the generator, right, that will destroy generator. Therefore, I must draw this and show you. Now, you can see, therefore, now water jet comes and you have the needle, you have the needle valve, right. Water jet comes and hits the Pelton wheel or whatever, right. And now this comes and overspeed this, right, overspeed this and try to destroy the machines. Therefore, we have a big steel piece here hanging, right, which can immediately drop on this, which can immediately okay. So, which can drop immediately on this, right, immediately on this and divert the flow. We call it a deflector, right. We use a deflector, right. Deflector is a big steel piece and it operates by the weight of that was hanging, not by electricity or hydraulic anything, because when the breaker trips, everything, all electricity supply will go. You can't depend upon anything, only by the weight. So, we have it will instantly drop and divert the water away from the turbine, thereby protecting it, deflector, right. So, deflector operates by this weight. So, both has can see both are having can see this weight, right. So, it is when the electricity is there, it is lifted up automatically and kept at a higher point. Moment the breaker trips, it drops and by that weight that steel piece comes down, right, and deflect the water away from the turbine, avoiding any overspeed possibilities, right. Okay. Here the tail race is done on the other side, you can see that is where it goes and join the river. So, they are covering it. So, finally, we put earth and completely covered entire area. So, So, you can't see any of these things. So, we can that's turf now, right, this area. So, we kept a mezzanine floor here, mezzanine floor, the upper floor, where you have the control panels and everything, on one hand to save the space, on the other hand in case this part is flooded due to whatever reasons, control system will be saved, right, control system will be saved. We can see various bearings here on both sides. Right. This is where the cables come out of the generator and taken through conduits to the synchronizing breakers. Here we can see now that is the concrete anchor where the penstock ended, right, where the penstock ended, and now it is entering the main inlet valve directly, right, main inlet valve directly. So, this is the synchronizing breaker for generator 1, synchronizing breaker for generator 2, and you can see after synchronizing the cables going in this rack to the transformers to the step up transformers. These are my engineers working with the equipment suppliers engineer who came to commission the plant. They are Germans. Now, you can see the tail race area is covered. Right. Here once we are finishing now almost. This is the finished look of the power plant. This is the canal being constructed. Sometimes you can't avoid a drop. So, there is a drop here because of the physical presence of the canal line. So, this is higher, this is lower. So, there will be a drop here. So, this is a flood day. So, it has blocked our some material that came here has blocked our intake, and that is why it is overflowing, and they are clearing it. This is the unnecessary overflow. This is the man-made overflow canal, right. This is the one that is in operation. You can see now there is a danger here. Now, normally there is no water here. Overflow does not happen every time. It happens when the circuit breaker trips or anything happens like that, right. Therefore, this is empty. So, when the people are moving about, when they want to take lunch, they sit inside here and take lunch, or sometimes people sleep inside because it is nice, no, compared to the jungle. But the danger is instantly water can come. There have been a death or two in Sri Lanka because people do not know, right. Therefore, you must have warning boards here all along saying that do not get into this canal, water can come at any time, right. Here you can see instantly, right, when the breaker trips, gradually water will be allowed to be overflow, right, not instantaneously. Deflector will first work, but then you will gradually let the water overflow at the forebay tank. See the overflow happening in the overflow canal. So, if somebody is sitting here, dangerous, right, when the water comes. This is a low head project. You can see in low head project what is the difference? H is small, Q is huge, right, because Q has to be large, otherwise the power is low. No? See the canal size, right, canal is huge, right, because you have to have high flow rate Q. All the civil components will be penstock components will be fairly big. See where the turbine is to be placed. The plant was under construction when we visited it. See the size of the civil components, they are expensive, and have to be designed correctly. That is why I said people prefer high head projects to be implemented first, right, and then medium head, then high, because the amount of civil work, civil construction components will be fairly big otherwise. This is a powerhouse. See the size of the penstock and the water entry pipes. This may be the tail race. Okay. Here are the 3 factories I visited for buying equipment, right. This is a factory in Austria called Gugler, right. He is Mr. Gugler, he owns it. So, I visited and inspected their turbines. So, these are Pelton turbines they have manufactured for various customers. So, they are monolithic construction, one piece, and then buckets have been machined. This Hitzing is a good generator brand. You can see sometimes they make for small machines the buckets separately, but I told you that this stem is undergoing fatigue failures because of the constant application of pressure and release, right. So, they have not been 100% successful, right, but still they are cheaper because you can machine it easier, you can put it to a lathe machine or a milling machine and use machining as much as possible using equipment. Otherwise, you have to do much of work in using labor. So, this is Austria. So, in the same visit, Austria is in the boundary of Germany. I visited a German factory to decide whether to buy from whom, but I later on decided to buy from this German factory. These are the photos that we looked at earlier, small machine and large machine. So, this was a turbine that they had manufactured for some other customer. So, this is a small, you can see micro turbine where they can insert this into this web and weld it, right, these buckets to make the Pelton turbine. That is for a small, maybe 10-15 kilowatt machine turbine. Maybe this may be the casing for that. Then for the second plant, 4 megawatt plant, I bought from India. This is Wijayapala India near Delhi. This is a German technology, they manufacture here under the license. So, the German people are present here for the quality supervision. They took us to a plant where they have installed their machines. I think this was in Mysore or somewhere I visited. This is their factory. Some Francis turbines they had manufactured for some other customer. This is not far from Delhi, maybe 10, 15, 20 kilometers, 30 kilometers away from Delhi. These are the hydraulic units that are used for the this control of the needle valves and other things. This is a deflector, you can see the steel part, this comes in between the flow, right. So, this can drop. Needle valve in the closed position. you can see this part of the case, unpainted part, has to go under concrete, right, has to go under concrete once it is installed, so that it is connecting and be integral part of the powerhouse. And this is the weight you can see for the deflect operation. And finally, in one of my visits to some area looking for power plants, we ran into this strange site where our power plant is completely destroyed, right. It has not been properly designed and implemented. Penstock and everything had been destroyed, right. I do not know the exact reason, but we were looking for sites and we were visiting some area where the rivers were there, and getting information from people, and then they showed us this. See, they have abandoned all the plant had been abandoned. They are my engineers who went with me. You can see they have not done proper anchors, right. At bends they have not done proper anchors, just put some concrete and just try to hold it. It will not work, right, that will not work. So, they have learnt a hard lesson. See, they are trash wreck, right, all are destroyed. Okay. I hope that some practical ideas what we discussed during the previous lectures, which will clarify your minds about hydropower and how they are implemented. And you know that doing this project is very interesting, right. So, it is in the jungle areas and new conditions, right, and so you make your huts and other things to initially, but later on of course, you build your own house or whatever, and but it is challenging and interesting. And when you are doing projects like this, that is where you learn, right. If you work in an office doing some engineering calculations and drawings, etc., of course, you will learn something, but real learning comes when you do projects. So, if you ever get a chance to do projects, therefore, do not drop them, right. Maybe it is difficult because you have to go to remote area, right, not comfortable as living in quarters or in houses here, but the amount of things that you can learn, I learned most of the things in my project life, not at the university as a professor. I learned lot of things when I was in the industry and did projects, and shoulder to shoulder with foreigners and working with them, learning from them and discussing with them, and all these opportunities come when you are doing projects. So, if you get opportunities to do projects, therefore, even if you have a loss of financial gains are not there as much as what we are getting otherwise, but go for them and learn, especially in the young days. Okay, with that we come to the end of our discussion today. Thank you.